everybody to the Open Group Conference. It is a wonderful week here in Philadelphia. We all have put our mind together from the Open Group, and we are attacking the problem, the challenge of how to meet our business objectives by getting the standards in place. And these standards have to be open, followed throughout the different players in the industry. So I want to spend this time with you talking about some of the things that I consider are cutting edge, emerging, taking embedded systems to the next level. I also, because of the release of my book, will quote a lot from that book also. So let us get started.
Okay.
So I thought we'll talk about it like that. What are intelligent environments? So my book is called Transitioning Embedded Systems to Intelligent Environments. So what is intelligent environment? That topic has been around for a while, but there is a new twist or a new flavor or a new way of thinking around it that I want to share with you today. And because this conference has a focus on health, and we thought we will talk about intelligent environments in health specifically. After that, I will talk about other intelligent environments as well, which include transportation, intelligent transportation, which includes smart homes, which includes smart grid subsystems, which includes energy and so on. And then the last thing that I would like to tie it all together is, of course, why we are here. What is our message? We want to be doing dependability and assuredness, and also achieve the goal of high assurance security. So what does it mean in intelligent environment? Of course, it means much bigger than it ever did before. That can be expected. So what are intelligent environments? So there are some things I want to start with. So in my mind, our human body is the best embedded system ever made. Perfect, right? Perfect. We got the brains, we got the CPU right there, and we generate our energy through the food we eat. We have sensors, eyes, ears, touch. We can do I/O, input, output, various ways of doing it, gestures, right? And all other embedded systems that exist around us are man-made, and they are actually emulation. They emulate the human body. Not as perfect as a human body, but they are good emulations. So that is the goal we go for. How do the embedded systems work? Well, turns out a human being can't work alone. I am here, I can't talk alone, talking to you all. The same is true for embedded systems. An embedded system in a dishwasher or in this box really doesn't do us any good until it works with each other to create an environment that is very intelligent and is responsive for us. So if we say that an embedded system is a human being, then if you take a virtual array of embedded systems, one can say that is an intelligent environment because it's all around us. These embedded systems are around us. They can expand infinitely. They can do work with each other, and they can do what we bid them to do. So that is why we call them an intelligent environment. So, and this is a quote from the book, intelligent environment is the intelligence that connects us to the whole world around us, whether it is here or across the world, or under the ocean, or over the clouds, or on an aircraft, or in a rail car which is carrying my milk. So I know whether it is in the right temperature or not. So it connects us with all things, whether it is in our homes, in our cars, in hospitals. That will be a big focus of what we will talk today, or even in our clothes, we can wear them. So we are always connected to these little things. This environmental embedded systems are connected to the internet with the web services. So once each one of them is on the internet, then they can interact as a standalone and as a group in a mobile wireless world. So you can stop me any point when you have
Here we go.
questions. So let us pick some health environments. How does intelligent environments help us in the area of health? So remote care is one of the big things because not everybody is lucky lucky, or even if you are lucky and you live in a place of wealth where you have the best facility, you may not have it by your bedside when you most need it. So there are a lot of things that patients or even not normal human beings need for their normal care that is not available to them, whether it is medical exams, medical monitoring. It may be after a heart procedure that you have to be monitored, or it is to diagnose what is your illness, or proactively warn you about something, or to treat them. All these things have to be available from remote, no matter where you are. So that is one of the requirements we look upon when we say intelligent health environment.
If you maintain this, you can sit here.
So we want to, whether it is doctors, nurses, labs, facilities, we may be out of hospital, but we should be able to be treated as if we are in the hospital. And also all the equipment, large mammography equipment or blood test labs, no matter where they are, we should be able to get it. So that's objective. Plus, this is the biggest thing, it should be in an invisible manner in our natural surrounding where we normally live, so that our life is not impacted just because we are sick. I mean, that's no reason to be sick is no reason to lose out on life. So what are the enablers? So we talk about all these things. What are the things that have happened in recent time that have made this a possibility? So one biggest thing is, and you will see that theme through, as I go through the presentation, and I talk about many Intel, like I worked for Intel for many years, and of course Intel is an HP partner. So most of the examples that I take use Intel hardware for them. Why? Because an Atom processor is one of the lightweight embedded systems. So because they're lightweight embedded systems, they were this lightweight before. So this transition, this transformation in the embedded system, in the CPUs have enabled us. The second thing that has enabled us, that the cords, the power cords become a thing of past. We have wireless technologies. The third thing that has made it possible is the medical devices that have miniaturized. For example, we used to give ourselves insulin injection and carry a whole paraphernalia. An insulin pump which is attached to the body is so small. We used to have blood test glucose monitoring machines, which was such a big machine that we used to carry with us. But now we have a CGMS, which is like a quarter exactly, which comes here next to the pump, and it is called a continuous glucose monitoring system. So this is amazing because, take an example, what is, somebody is a diabetic and needs to take insulin. What is it that makes him different? Am I too fast? He's my mentor. So what is it that makes a diabetic person different from all of us? So they get insulin, they eat food, but the feedback system for us who have a normal pancreas is automatic and immediate. So when we eat, our pancreas, beta cells know exactly how much, islet cells, they know how much insulin to produce. A diabetic doesn't have that benefit because those cells are destroyed. So they have to take insulin. So what do? They have to do one technology on one side where they have to measure how much is the blood sugar. Based on that and how much they've eaten, they have to make a decision how much insulin to take. So two machines, and there is a human in between. The CGMS and the insulin pump combination eliminates that. The CGMS automatically on a continuous basis throughout the day keeps monitoring the blood sugar level. The insulin pump keeps delivering insulin not in 2 or 3 shots in a day, but in a very minor basal level throughout the day and night. So the advantage of this technology example that I gave you is that they are almost as good as a normal human being whose pancreas works perfectly. So that's a beauty. So if there was no wireless technology, these two things won't be talking to each other. Actually, the beauty is, although they are next to each other on a person's stomach or waist, they are actually talking through a server. They are not talking to each other. They go to a server. The server makes the decision and tells the pump how much to give. So that's amazing. The other thing is the connectedness of medical devices, which is what is an example of what we are talking to each other. So the fact that different devices are able to talk to each other. So if I am carrying EEG, almost invisible, small, instead of carrying big leads and lying down in a hospital bed for electroencephalograph, if I am carrying a small EEG device on me, then because they are connected it can immediately, if there is a problem, they can immediately alert the doctor in the hospital that so-and-so patient is at the risk of seizure, and their life can be saved. So the Bluetooth connectedness helps there. Bluetooth biometric sensor is another big deal, because one is that it measures all the biometric data of your body, the vitals, as well as everything else that's necessary for a normal human being functioning. And the Bluetooth in a short distance is able to send that to another device that is able to listen. So that enables a machine-to-machine communication. The one last thing that I feel has had a big impact is wireless sensor networks. So how is it different? We talk wireless, we talk sensor, and we talk networks. How is WSN different from wireless plus sensor plus network? It's more than all three. And it is actually each one of the node in a wireless sensor is a computing device. It has its own ability to generate, it has a small power in it, it can work for a certain time, and when the battery die out, you don't have to recharge, you don't have to service it. It has the ability to service, and they can talk to each other on a network. So how do you use it? What's the advantage of that? You can take a truckload. I said truckloads, what I really mean is a lot of little grains of wireless sensor network and put them in remote places. Suppose we are measuring the temperature gradient inside the ocean, or we want to measure in certain forest, we want to see if there is some forest fire or some sudden change in temperature that we need to wake up about. So these little things, computing devices, wireless sensor, they are thrown out there. All of them are charged. They are configured so they can talk to each other. And they build ad hoc networks. So obviously some of them will die out, some of them will outlive, some of them will get the data, others won't. And they will dynamically build the pathway through the network till they get to the server of some kind, which is getting all this data and is able to make sense out of that, fuse all it together and make sense of that. So wireless sensor network is, to me, the most mature of all of these technologies. So mobile care, let's talk about mobile care. So many unfortunate, when people are sick, when they are in hospital, they're taken care of. When they are at home and they don't have a problem, they don't need as much. But sometimes when you call 911, an ambulance comes and it takes you, so many unfortunate deaths happen on the way. Many reasons. They didn't know this person was in a friend's place. He fainted. You don't know it's a drug overdose or it is a diabetic patient who is going low. If you try to give him sugar and he's already high and in a coma, you have another problem. So because of lack of, so the issues that can be solved or need to be attacked is there a lack of our ability to get information about this patient? Is there a lack in our ability to do different tests, or is there a lack of our ability to talk to somebody outside and figure out what we should do with them? So that's mobile care basically. So emergency medical teams carry wireless medical systems now, which are in the intelligent environment. They carry medical systems that are connected. They have, doctors can remotely, even when they're on the way to hospital, look at the person's vitals and give an advice on how to fix it, or what is the immediate care to be done. Or sometimes it may be, don't bring them there, this person needs to get a heart catheter done, we don't have the facility, can you please bring them to the other hospital. So, and they also have diagnostic tools, so they can actually diagnose, they can take a blood sample while on the way to find out and talk to doctors and find out what action should be taken. So some of the machines that have this connectivity to the labs are ECG is one, and that's very critical because the heart function is one of the biggest things on which we are on a short rope. We can't, we don't have much leeway when we have a heart problem because the results are drastic and immediate. Stress test machines are another thing. You can do a stress test anywhere and they can be connected to somewhere else who is analyzing these tests. Brainwave monitor is another thing because it's not good enough that you go to the hospital, get your brain's waves measured and come back because you may have a problem after you come back, and therefore this will continuously monitor. We talked about EEG. blood test meter and insulin pump, we talked about them. So these are some of the areas where mobile care is enabled in intelligent environments. Personal devices is another one. So there are some big equipment that is in the lab, and there are some small devices that can be on a person. So this one, on this slide I talk about that. So for example, there are embedded medical devices that continuously measure biological levels. It may be continuous, or it may be as the doctor deems necessary, or it may be proactive heartbeat, which is very important. Continuous monitoring of chemical levels in the blood, that's important. If you had a viral infection, what is the state? Is the virus getting worse, or is it getting better? To monitor that. Also, if if your EEG is performed on a regular basis, you would know beforehand if a seizure is going to happen. So these are the some of the biological levels that can be measured, and of course this is a very small list of others that can be measured and acted upon. We talked about wearable medical devices. Why is it so important, right? I talked about insulin, and I talked about insulin pump. We talked about other things. Because when people make mistakes, in the hospital, people are taking measurements, they make mistakes, and therefore, if somebody tests manually, true story, right? Tests manually and says, oh, he needs insulin, and put 1 U, like unit, or 4 U, and somebody reads it as 40, and they get 40. I mean, this is a true story, happened. So this reduces that. Also, the lab microscope. So one of the big things is when blood test is done, microscopes are used to do that. So having embedded systems inside the microscopes that have the intelligence to do various things. One is to take the sample and remotely present it to a lab somewhere else, analyze that image, to be able to look at that image and analyze it with the small embedded system is a part of intelligent environment, and compare it against the database of known diseases. Or if it doesn't match any of them, then raise an alert and say, we don't know what it is. Or transfer results to a doctor for review. So those are some of the things that can be done in intelligent environments. So this is again, we talked about remote emergency doctors, and this is going down. So I spoke at a high level, why we do what we do. Here we go more into detail about the nuts and bolts of how it is built, right? So this is what I used to do in Intel. I was in the Intel architecture group as a platform strategist. So I was building platforms, so this comes naturally to me. Intelligent, and hence Joe's joke that, do you know any other chip maker? Will have you meet other chip makers? As if there are other chip makers at Intel. Of course, I'm joking. So intelligent, so on the left, what I've tried to do is, what are the technology components we need to make a solution work? So this is the solution, we talked about it. On the right side, I've taken some examples of the chips. So they can be changed. Instead of one particular technology from one particular vendor, something else can be used. So when there are first responders, and they come to treat somebody at their home because of emergency calls, then if they have a heart condition, you want to be able to quickly diagnose that this person has a heart condition. I'm so sorry you have to stand.
No, it's fine.
We can get chairs from the other
We've got a couple chairs coming.
Oh, you? Okay.
I sat for 3 hours, so it's good. Stand up.
But I'm grateful that you are standing and still listening to me. So we want to minimize the time it takes for the results to reach the catheterization lab. Because if you take them, if you need to put a catheter inside a heart, it's time sensitive. We need to do it like yesterday. And by the time you take them there, so we want to make sure that from remotely, a catheter, one can do the diagnosis of heart condition. We can also make sure that the time taken to the lab, catheterization lab, should be minimal. Plus, not every hospital has the right kind of facilities for the situation that is there for this particular patient. So that kind of diagnosis analysis can be done by embedded systems. In intelligent environments, within the ambulance. So an ambulance itself can have all these facilities by which this can be done. Then the right EMT can be selected, the closest hospital can be alerted that this is happening, and also because their GPS systems are there, they can automatically route and alert, see the current traffic and make sure that the best possible route is taken so that the person needs treatment. So these are the solution and components that we want to build. So what we want to see is that from Intel Core 2 dual processors. So this is a case where we need a little more than just a wireless network, sensor network computation, because this is a little more intelligent. So based on that, you will see that I pick the kind of high-end or the low-end hardware. So here, Core 2 duo processor plus a touch screen computing device is needed. Atom processors can be used to collect biometric data. So there can be many such different devices for all kind of different biometric data. We can use atom processors to collect and analyze and transmit data. But once the data is transmitted, then it takes a stronger processor to be able to put it together, analyze. Remember they said big data. Big data means different things to different people. Here it means our ability to process it and immediately take action. Also, there is the security this thing. So there's a Intel Trusted Execution technology that is there. And what it does is there are many hardware extensions that protect. So medical data is very, very sensitive. You can't share with each other. So you have to make sure that they are in silos. Nobody can look into each other's silos. Intel Trusted Execution technology helps us do that, protect that, and also prevents software-based attacks. So let's talk about some other health environment things like pedometers, right? We always had a pedometer which would measure how many steps we walked, but we want to take that a little further, make it like a bandage on the body, and then continuously report the heartbeat, heart rate, daily calories, and the body temperature. That's very necessary for a healthy person who is doing an exercise, because you don't want him to run into some kind of a. So one of my Douglas Adams, it's a science fiction writer. He was on this. He was 42 years old. The Hijacker's Guide, right? He was 42 years old. He was on the treadmill and he died exercising. So things happen. So we have not fun yet. No.
So we should
I don't know
not
why I'm
exercise.
laughing, but not funny. So the point is, lives can be saved, right? If you are able to, even if you're healthy or another thing, you have a pedometer, but in an intelligent environment, it should be smart enough to find out your heartbeat, to find out the calories, the body temperature, and things like that. Hearing aids, right? So we've been using traditional hearing aids to increase the volume of things that people cannot hear, or to go to that part of the ear that is functioning, so that even the person who is not able to hear can hear with the hearing aid. So we want to take it to the next level. People like me, right? I have an accent. People like me, I talk very fast. So what if there was an accent neutralization chip in the hearing aid, or if there was a slow, like amplify, like half the speed or whatever I say. So wouldn't that be nice? So if somebody had hearing aid and you could have accent neutralization or any other thing, right? Big thing is if there is a visually impaired and there is some hazard going on, they can't see and they can't hear, then the alarm they can't hear. So if this is a very key thing, if the hearing aids had the right kind of embedded systems in the intelligent environment, they can immediately, they can be connected to each other, and whenever there is a problem, yes, please come, welcome. Then they can be informed. So that's really good, because then the deaf people have a sense of security. This one is another thing, the robotics, right? Human robotics. So we have, limbs. People have accidents, lose part of the body functions, and through technology we try to fix that. If there is a paraplegic, then we can give them prosthetics. But there are ways by which they can be made fine so that they are very natural to the person who's wearing it. For example, if somebody broke his ankle and needs to have a heel or some part of your foot replaced, and you have a prosthetic feet, and you have embedded system there which is actually taking the energy, because the requirement of the foot is different from person to person. For one person, only 20% of the feet works. For other, it can be 50%. So if there is a continuous sense of how much the bounce is and how much the person is able to move, and we can calculate how much is needed, then the robotic muscle for the paraplegic will be as good as a natural thing, not like a crutch to wear. So it is, the other big thing is it is powered by the body's own energy. So this is one of the things I'll talk about even later, because harnessing of power is one of the big things in medical devices and other areas of intelligent environments, that the energy should be there from the environment itself. So for example, wireless sensor networks, we throw them in somewhere in the desert. How do they power themselves? Can they do it from the atmosphere? Because if they can through the environment, we are done. We don't have to worry about that. So these are the two features of a robotic muscle. It works very well because it takes energy from the person's own feet, and it is able to adjust it using the intelligence as to exactly how much correction is needed, which is very different for different people. So clinical care. So doctors also have to talk to other doctors all the time, right? So they can use video conferencing and other ability. So in intelligent environments, because everything is available on network, all information about the person is available. They can consult each other. They can see the results of various labs and collaborate. So that really helps. So you can go to a doctor and you can immediately consult the orthopedic, and rather than go back, go home, and give your referral, come back, go to another doctor, get another 2 weeks later appointment by the time the person dies. Not like that. So also the digitized health records, we have had that for a while, but we can take that to the next level and say, okay, not only do we have a patient image, but we have all the medical images from blood sample and everything else that has been taken, and into the picture archiving system. And these pictures don't have to be taken by sophisticated, specific medical equipment, but by ordinary digital cameras or sophisticated digital cameras. So imagine if there could be a mammogram that can be taken in rural areas where women don't have that facility, through using digital cameras that are specific for medical use. That's a big advantage. So the other kind of mobile healthcare is text messaging. For example, if you remind people about the medicine, you have to take your medicine at 3 o'clock, take 3 pills. After that, after surgery, or about your appointments and your other care plan activities. So that's another area where it will help. So this is interesting, right? Pills with edible computer chips. Now we are getting smaller and smaller. Chips are getting smaller and smaller. And we take medicines in pills anyway. They're coated. It is antibiotic powder. It's coated in a plastic thing. So if we can put a chip inside it, which has some kind of identification, radio frequency identification data, and a person swallows it, then it is always communicating. It's in your bloodstream, and it is in your body, and it is communicating with the doctor. So for example, if you had a skin patch, then you can send that signal to the doctor. Or if you went through some, let's say, cosmetic surgery, and then Kanye West's mother died after a complication of the cosmetic surgery, because she came back, doctor said fine, take rest, but that was not the right advice, because she had a heart attack soon after. So now if you had a bill like that, you can always monitor for adverse reactions, because adverse reactions only happen in 1 or 2%, but when they happen, they have very severe consequences. So we talked about how doctors can save life from remote. So let's see how we can implement and actually build this scenario. With some example, there are of course various ways to do it. I just picked one. So what is needed here? So let's kind of articulate what are the things we are looking for in this solution. We want to make sure that the biometric data is available in real time, like as it is happening. We don't have time to waste. We want to make sure it is transmitted over a wireless network. We want to make sure that doctors have the ability to advise the ambulance crews with it, whether they are at home or on the way in an ambulance. We also want to make sure that the ambulance can itself figure out what is the best route or the best place to go to take care of the situation. We also want to make sure that the remote diagnostics can be done. And there are some people on the other side, medical professionals, who are continuously looking for this data and telling us how are we doing, if there's an alert or not. And we also want to make sure that there is, because these devices are mobile, it always comes down to how long can a mobile device live, because it is dependent on how much power they consume. And the more power they consume, and given a certain battery lifetime, they will die. The devices will die after the power is gone. So these are some of the ways we want them, the emergency technician, to be able to collect data, collect sample and transmit them. So these are the requirements of the solution that we are building. So let's look on the right as to what are the technologies we should pick. As you would see that I always pick a Core 2 dual processor based system when it is medium work, but not very intensive. Of course, if it's very intensive, then it's a whole different story altogether. But again, it cannot be as simple as a base atom processor, because that has, it will take very long to process that data. So that's why I picked one with dual processor and mid-range, right? So the mobile application, the advantage is that because it is an Intel-based architecture, although it is small, one of the biggest problems with the Intel architecture was they had all these powerful big systems, and they only worked on what was called an Intel architecture. So the small chips, it was very hard for Intel to actually accept and start working, because for them to work in, when you have a legacy code that works for such a long time, and it's been like decades, nobody knows how to cut off some code and still get it to work. And that was the problem with making smaller chips. How do you do that? Because if you cut off pieces of code for a small chip, then we can't get it to work. So this was actually a big breakthrough from the hardware perspective, which is actually a real reason with Atom and Core processor that Intel actually started making its mark in the embedded systems market. Because for the first time, their power requirements were small, and they actually worked with Intel architecture. And because they work with Intel architecture, you can blindly say, okay, all Intel software, Microsoft software applications will work on them. So that's a good thing. It's not proprietary. It's not something that's off the shelf that you don't know whether certain applications will work or not. See, the other thing is that energy efficient performance is needed for us. So Intel has an active management technology. That is very important for this. Why did I pick that? Because AMT, it's called AMT, but it's active management technology. It's really managing the system, but it's managing actively. What that means is, it has one big thing. It can manage, of course, fleets of different computers. If you're sleeping, it can wake you up. That's one of the big things about AMT, which is how you need. If you want a low energy system, you don't want your processors to be awake and always saying, oh, is somebody asking me to work? They can go to sleep. And when there is a trigger of some kind, then the AMT technology will go wake up the processor and get them to work. So that's a beauty. You only use the power when you are needed to, and then go back to sleep. And the other is the trusted execution technology. So that takes care of the security piece of it. It protects the integrity of the data that goes through the system, which is really critical in such an application. So let's talk about infections. In recent times, although the number of infections have reduced drastically over the years, as our understanding of human body and the sicknesses that plague it have gone. However, there are still some infectious diseases that hit us, and when they hit us, we are just not prepared, because it's a new case, it's a new virus, it's a new bacteria, it's a new strain of something. So we want to make sure that when these things happen, because they will happen, it is only a matter of time, we contain it, we make sure that it doesn't spread. And how do? We want to have portable lab kits for remote labs. That means just like you can carry a thermometer with you. Everybody has a thermometer at home. Medical professionals will have some kind of temperature sensing, but we take that further and we say it's almost that they have a remote lab kit with them. So no matter where they are, they always have a lab kit by which they can actually do all the testing as if we are doing it in the lab. We just covered that earlier. This is another application. So because of that, so if there is some outbreak somewhere, you can go there and find out who all is having a problem, get them analyzed, and then figure out if there are some new diseases that have been either they have been identified or it's a new one, and then actually work on it. So blood samples can be submitted remotely. And how is that done? So basically, a very high resolution photo micrograph is taken of the slide. So when we have our blood in the slide, it is just very high photo micrographs of that blood sample picture is taken. And because earlier we couldn't do it because it had so much data in it, because can you imagine if you have the more pixels we have in a picture, the bigger our size of the JPEG file becomes. So you can imagine if we have the more and more resolution we need more and more data. But now, because our computers have become more powerful, it has now become possible to do that. So that's a good thing, we can do that. And we can send it even over a cellular network or a satellite uplink, which means that we can send it over the phone or a satellite to analyze it via pathology lab in the medical center. And that way we can contain our infectious diseases. So let's see how we will, now let's get in the mode of, let's build it. We know what we want, let's build it. So what do we need? One, we need a virtual lab doctor, right? We need a technology solution which is a virtual lab doctor. What should they do? They should have wirelessly connected diagnostic tools. And what they should do is they should connect to the portable microscope kits. So microscopes that are connected, that have an embedded system that can take camera and send pictures. And this is linked to Microsoft. On one end, we have the microscope, which is portable, and in one's hand, there is a USB camera. So if one has a higher resolution camera, you can use that. Less resolution, you can use that. And then these digital pictures are taken and passed on to the embedded microscope for analysis. And this embedded analytics is used. And what is done is, once this data is done, there are special markers for each kind of infection. For example, malaria, of course, it's all but gone. I mean, malaria is almost a thing of past, although we still get surprised here and there in the Western world. So there are special markers that we can see for that and see if there has been an outbreak of that. There are other also blood-borne diseases that can be seen by this remote microscope. And after the report is generated, it is encrypted into an email and sent to the pathologist, who can then take action and say, hey, do this, do that, or whatever. Or quarantine this person because this is the biggest strain of something, plague maybe, which we didn't see. God forbid, not happening, but I'm just giving an example. Something we didn't see for 5 decades, but it's coming back. So what are the enabling technologies by which we can build them? So we need medical imaging device. That's one thing we need. And we need a very good one here. It's not just enough to have internet connection. It's not good enough to have small power requirement. We want to have a very good medical imaging device, so that we can have ECG monitor. We talked about blood sample, even ultrasound we should be able to send it and process it. So again, we look to secure that data by trusted execution technology, which is called Intel TXT. And what that does is, as I explained, isolates your information from others. So biomedical science, we talked about many, but what we want to do is we want to make sure in hospital, whether we are at home or we are on road, we should be able to have biomedical science always should be visible to the doctors or the medical teams that need to see it. We should always have, and the environment should be able to program vital signs, which is heart rate, oxygen saturation, ECG data, also raise an alert condition. If the oxygen level is below 80%, we know why there is There has to be a reason for that, and immediately the doctor can be alerted. That this controlling of infusion pump is another big thing. So we talk about a person always controlling his medical device. So it's a personal medical device. Sometimes it is necessary to control it from far. For example, the firmware may have changed. It has a new software functionality. So the ability to control an infusion pump far away is a very big advantage. Then we can also monitor a person during surgery. So let's say the surgeon has done the surgery and he has gone, but the person is still in the operation room, and his sensors and actuators that will automatically transmit data to the surgeon. And the benefit of having machines measure it is that machines won't make mistakes like human beings will. And also the other thing is, patient doesn't have to be restrained to the bed. He can walk into the corridor and meet his visitors, and all the while his biomedical signs are being measured. So we definitely need, this is a biomedical WSN. So WSN is the key, right? Wireless sensor network. Why are we using network here? Because now we are talking about a whole set of biomedical signs that are around a person. We're not talking about here, this, that. So it's better to have a network of sensors that measure different body statistics that can talk to each other and figure out if everything is working okay or not. So this is a very good application of having, and because you have to carry it on the body, you don't want them big, you want them to be small, small, small. And it's like throw a dust of them on a person, and some of them will fail, some of them will work, and they will talk to each other and make ad hoc networks, find dynamic routing paths, and report the data. So it's almost like a body, like LAN is a local area network. It's almost like a body area network because they measure all the body's biomedical signs. So one thing here is now we are dealing with many applications. We are talking about after surgery. So all the blood related applications, all the EEG related applications. So there are many of them, so they have to be consolidated on a single platform. Otherwise, one doctor has to deal with so many different applications is another issue. So we want to solve that issue. Plus, we want to make sure that there is code and data separation. Many applications don't all work in different operating systems. Some of them work at a different level, some of them work on a different hardware. So because we might need multiple operating systems, we might need multiple layers of hardware. So this is an example where a complex solution is built to meet the need of full body scan of a person's biomedical information. So how do we do it? Virtualization technologies. I haven't talked about it, so I was dying to talk about things else, virtualization technology. So there's intermediate. Why do we need it? So okay, when you do virtualization, you always have to have a hypervisor software. So basically what it is that you can have, it's a separation but it's very different than the TXT. By virtualization, you virtually partition the application and everything that is under it, whether it is the code or the data or anything with that. So it can be many to one or one to many, which means that many different applications can be virtualized to look like one, or sometimes one particular hard disk can be virtualized to look like multiple, or one particular operating system can be virtualized to look like many. So there are many instances of how we can use virtualization technology, but this virtualization technology with the hypervisor for wireless sensors will help isolate each person's so although it's one doctor here who is getting data from 10 different patients, but they are isolated and there's no mixing of those data. So that's very good. The other thing is that we want to provide hardware protection. So one of the biggest virtualization that happened is over the years is that we virtualize, we have layers and layers. We virtualize the CPU, we virtualize the RAM, we virtualize the storage unit, we virtualize the applications, we virtualize the memory. As we do all this layered approach, that we are not neatly slicing it. So this is this helps us. So although you may say we are very virtualized at the top layer, but at the bottom layers we may not be. So this helps us make sure that not just the top layers, but all the way up to the hardware is completely virtualized and separated. So, okay, invisible devices. Why do we want devices to be invisible? Because sick people don't feel like looking sick, right? If I'm here, I don't want anybody to know I'm dying of, maybe I'm just dying, blood cancer or something. So, because it gets in the way of you living a healthy, a normal life. We don't like it. So, invisible monitoring devices help with that. And the technologies that help us is we have lightweight, wireless. If heart patients had lightweight wireless EEGs, brain patients had the EEG and the heart patients had ECG. Let's say the knee braces that we get after an accident, if they have motion sensors, then what is the advantage? You got a knee brace and it is sensing the motion. And based on that, it is monitoring if your foot is working okay or not. And then if you are taking exercise, or if it is some cartilage was repaired but it is found that that cartilage is broken and the motion is going all the way here. So there is a trajectory of the operating parameters that are expected, and there is a reality that is recorded and sent. So that difference can alert the physician. So that is an example. The other example is digital mammography. So mammography can be done in remote areas, but the specialist in a hospital can read and give advice on them. So those are invisible devices, or even mobile vans, which is kind of a different flavor of invisible devices. You don't have to go to the hospital to get mammograms done, and you may not be able to because that may be 1,000 miles away. So here the problem is a large data set. Each scenario that we talked about had a unique twist to it, had a unique problem that we were looking at. So the problem here is a large data set. So imagine EEG scanner. It's measuring over the day, overnight, every minute, every second. So that adds up. And if you're doing it for multiple EEG channels, we can have 64 data channels. So we are talking about a lot of data, a lot of processing power that is needed. The other thing that is important here is that was not true of everything else. We said, let's just get the data, let's send the data, somebody else in the remote has to have big processes and lot of intelligence to analyze. Here we are saying that right there where the EEG data is connected, we need to put some intelligence there. Why? Because if we put some intelligence there, we don't have to transmit a lot of data. And so that is done by a small footprint atom processor which have energy efficient performance. So by doing, so this is an example where we need multiple grains, but each one of them can be a standalone computing unit, and multiple, a fleet of atom processors can be used so that the data is gathered, analyzed, and then sent across rather than being sent to analysis. So it's a different scenario. So we talked a lot about medical. I also have some more. I can go into as much detail or as little detail as you want me to. I do have many of them here, and I will just based on how many people are sleeping, how many are awake, how many are shaking their heads or not shaking their heads, decide which slides I want to skip through. So here, energy management, not medical, different page, right? But very similar concept. So why is energy management so important? Because once we have so much intelligence, each one of them are processes, each one of them needs brain power. And who gives them brain power? It has to be a computing element, and that has to be powered. And therefore, the issue of energy management becomes big. The other thing that is there is that how do we make sure that these solutions have the least energy management? So here we take an example of a building. It's a big building. We want to make sure that the utilities bill for a building contractor is minimal. We want to make sure that people are comfortable with the right temperature, with the right air pressure, but at the same time with the right level of humidity. At the same time, we are not wasting energy. So how do we do that? So we put little low-cost battery-powered wireless sensors all over the building. 10 here, 10 here, 10 here, all over the building, and then you leave them alone. And nobody has to actually go and sense it. And we can measure temperature, humidity, as well as the lighting, because we may not need all these lights, or we may need double of these, depends on that. And so what happens is these small sensors, they talk to each other. Again, because it is a wireless sensor network, we know that they do multi-hop, we know how they talk to, they know how to talk to each other. And then what happens is that throughout the building, these little networks, they talk to each other, they figure out and send the data to another server router system. And there has to be a server somewhere outside who can manage this network and gather the data and know that this room, that room, that room, that room is at so-and-so temperature, pressure and humidity level. And then actuate from there, the control of all these energy points are controlled. And actuators are used to change them, modify them. And that level is sent through the network. So what happens is, when all this data is collected, when we put them together, it is called sensor fusion. Fusion because we are fusing different sensors from different places. So that's the concept, how we manage energy in a building by using wireless sensor network. So on the right side, the fact that we are using atom processor, here we are saying Z file XX series. Also, we are specifying the SCH. SCH is the controller hub. SCH is like a sister to a processor. The processor computes it, and the SCH takes care of all the control thing. So a SCH hub, it's a hub, so it hubs to all the system control. So they use different power. So this is a 15 watt power, so that's very little. 15 watt is a very good SCH hub. So that's why we want that. And the good thing about this is that you can also do a IEEE 802.15.4 mesh network. Why do we need IEEE 802.15.4? Because that's the mesh network standard used by the wireless sensor networks. So this feature allows us, the other beauty of this is, why do you think it is a US 15 watt system controller hub? It doesn't use a fan. So because there is no fan that is needed, because it doesn't get so hot in the first place, the energy, there's no mechanical thing to move, so the energy consumption is very less. So that's how we manage the power in our building using wireless sensor network. Of course, as always, we need a server somewhere else which should be able to analyze all of that. So we do need a gateway server router which has more processing knowledge, and it can deal with. It also should have a flash memory that's needed on chip. So Intel's new flash memory is what is.
Question on the left side, sorry. How many devices can you get? How many ports are on that hub?
Oh, the SCH, different ones have different, but here we are saying 1:1. This one is 1:1.
No, but the
hub itself, the fan out of the hub, the different configurations.
How big?
So all the GPIO devices, conventional IO devices can go to the SCH hub now. So it is one signal that replaces all the GPIO, the USBs, PCI Express, all of them together in one.
12 and 15.
How many?
12 and 15.
Okay, got it.
12, 15.
And they're different configurations, so you can pick and choose which one matches you. But the minimal requires basic IO, and then you can get fancier and fancier. So the older ones, for example, have the older PCI interfaces. The new ones, the new hubs have the new PCI interface, but they require more energy. So then you can say, oh, I don't want that, maybe I can. For me, energy is a bigger requirement, the number of outputs. So you can have processor memory and a flash memory storage. So I hadn't talked about it so far because we never had a scenario where we will need storage on the CPU. Because if we are using an external storage, then we are wasting time talking to the storage, trying to get the data, and then act on. So if the light, we need light now, suppose it takes us many cycles to get the light turned on here. What's the point? It's not convenient. Therefore, we decide to have flash memory storage as well as radio components. Radio components, of course, are needed for the Wi-Fi. So smart grid. So this is energy, but in a different way. The first one that we talked about was how do you look upon energy in a building. here it is as a smart grid substation. How do you do it? So here we have again a network. Why is it smart? Because we have different, when we say network, grid network, we know that it is a array of different nodes that are there. And what are those nodes? Those are different supply points. For energy grid, the supply points and the points where the energy is consumed. So we want to make sure, in real time, we want to be able to monitor it and say how much energy is needed where and what are the points by which energy is available, and make a smart decision to route that. So what that means is there are substation units remotely. Each one of them will have to be on IP. Because if they're not on IP, they're not on the grid, they're not on the substation, then they become part of some bigger thing. So it's not good. And why is it meaningful now to talk about it? Because now, as we said, one of the enabling technology was that everything is now IP enabled, right? Everything is now connected easy. So because of that, every substation is on the IP network. Even the smart meters at home, people have smart meters which measures how much you are using at what point of time, which communicate with the outside supply. So based on the dynamic usage, based on whether it's offline or online, the cost of energy may be different. So if I had a smart meter which told me that the rate of electricity for your washing machine is 3 times more than what it would be 2 hours later, of course I'll say forget it, don't do it now. Even though it's just maybe $2, but nobody can resist that. So overall that adds up to conserve energy usage, the footprint of energy. The other thing is we can also regulate voltage level. So in all the smart grid, we can figure out how much do we need from its substation. Based on that, we can control the voltage, the right level of voltage that is needed to provide that. And all of this, that is nothing but an IP-based network. And then the beauty is, as you have seen, as we did with medical, as we did the IP infrastructure, the computing infrastructure is all the same. What changes is the endpoints. So instead of measuring human biomedical things, here we are measuring the capacity and the usage of the electric grid. But the back-end infrastructure is the same, so it can be reused over and over again. They use the same standards-based protocols, and that's the beauty of being in open group, and we are the ones who author that, right? So we can see how it impacts the way intelligent environments are evolved. So the moment we put in some technology, we immediately can put in 10 more of them, with just the endpoints are a little different. So this smart grid again uses reusable components. When I say reusable component, I mean the IP infrastructure, the networking infrastructure, the sensors are different. So what are the enabling technologies that we can use here? So one of the ones that are very important to use here is industrial PCs. I never talked about industrial PCs before because this is the first example where we feel that this might have to be, it could be, for example, controlling a wind turbine. So all kind of harsh conditions. So therefore we want to have industrial grade systems, which for every Intel processor, there's also an Intel grade processor available, which is the more sturdy version in a different packaging dimensions, which can take more harsh conditions. So then here we need certain very important things. We have to have fault detection devices. We have to be able to see which grid went down and how to make, if one grid went down, the others can immediately fill in, jump in and make up for the loss of one particular point. And so that fault detection devices have to be there. There has to be ways to monitor the quality. How do you define, how do you know that certain system has gone down? There has to be power quality parameters that are measured. You should be able to say if your current levels are beyond this or your voltage levels are beyond this, then we can say that this is not acceptable quality of power, and therefore we are going to bring that down and take corrective action. The other thing that is there is that we also need automation switchgear. The automation that is used here, the automation means not every substation used to have as much automation before, but now that you're putting them all onto the smart grid, we need to have those automations on each system in place. Because how can you control something that cannot be automated? If you have to, at the end of the day, go down to the system and manually turn switches up and down, then it's not helping our cause. So Intel AMT is, we know that, for isolation. again, there is also Intel MP System Defense Manager. So this one is important here because this is a risk for threat. This scenario where there is a lot of energy, one is tempted to hack and start consuming energy at some point by hacking the system and never have to pay for that energy. So Intel MP System Defense Manager is there, which can log the threats and make sure that outsiders don't get in. And if there are some clients that are infected, this automatically allows you to isolate those that are infected so that the rest of the system can